Hey everybody, we're here to talk to you about benchmarking today. I'm Chris.
And I'm Dustin, and we're engineers who work on Android toolkit stuff. So first, I'd like to start off with a note. We're not here to talk about benchmarking devices. I know a lot of people out there are probably really excited to compare phone A to phone B, but that's not what this talk is about. This talk is about benchmarking Android app code, specifically Kotlin and Java-based app code, and a little bit of NDK code too. So what is benchmarking? There's probably a couple definitions out there, but for all intents and purposes of this talk, we're talking about measuring code performance, right? We want to know how much time it takes to run some chunk of code. And we want to measure this in a way where we can see our improvements reflected in those measurements. And of course, unlike profiling, we're not running the full application here. We're looking for a tool for rapid feedback loops. We want to iterate and quickly. So, you've published an app. Very exciting, right? We're going to be rich and famous. And then your users start writing reviews. So first, 5 out of 5 stars. We're doing great. Hearts in the eyes. Was this review helpful? Yes, for my self-esteem. 5 out of 5 again. Awesome. Little hesitation space. Exclamation mark. We're doing great. And then the inevitable 1-star review. Lag. Ugh. You're so upset you can't even spell it right. Well, we've been there too. And we'd like to share what we've learned. So let's go on a benchmarking adventure. Very exciting. We'll start off with a test. We'll call it My First Benchmark. And here's an object that we might be interested in benchmarking. If you haven't seen this before, this is the Jetpack Work Manager library, and it's basically an abstraction over async tasks. And here's a synchronous test API we can use to measure. So what's the first thing we might do? Well, we could get the system time, and then get the system time after we've done the work, subtract that out, output that as a result, and great, we have our first benchmark, right? We're done. Well, not quite. We'll find that as we run this over and over again, we'll get vastly varying results, and that's no good for measurements. But what if we ran it in a loop? And maybe we'll run this loop 5 times, and then we'll report the average. So great, problem solved, right? There's still a few issues here. Well, first, 5 is kind of like a random magic number, and ideally we'd like to dynamically compute this number. We want to report the result when we're ready and confident that this number won't change too much. We're also measuring immediately. And the issue here is that the first couple runs of some piece of code might not be indicative of what the real user will experience. And this can be due to code paging memory or just-in-time compilation optimizations. And we're also including outliers. So everything on device is a shared resource. And this can cause complications, background interference, that might cause certain runs to be much, much slower than they should be. And if we include those results, our measurements will be completely off. And make sure we're not running an emulator, right? Because while it's very tempting to run tests in an emulator, emulators don't emulate real-world performance. So the lesson here is that benchmarking is tricky. It's often inaccurate. We're measuring the wrong things at the wrong time, right? It's unstable. There's tons of variance. How many loops should we run? And it's hard to set up correctly. That's worst of all, because benchmarking is a tool to help us focus developer efforts. So it's hard to set up how much time we're really saving here. So I'd like to introduce the Jetpack Benchmark library. It's out now, and it's in Alpha 1. And this is a previously internal tool that we've been working on for years. But we've been working really hard to get it available to the public now. So we hope you guys will enjoy it. First, I'm going to go over a little bit about what it looks like and how you might use it in your code. And then we'll talk about the internals and how we solve a lot of these issues. So Jetpack Benchmark. It's a tool for measuring code performance. Of course, thank you. We like to prevent common measuring mistakes. There's a lot of common pitfalls that we've seen in the past, and we want to pass those lessons on to you. And best of all, it's integrated with Android Studio. Who doesn't love Android Studio integration, right? So let's jump back to our previous example. Here's our previous benchmark. It's verbose, and it's full of errors. But this is really only the code that we care about, the highlighted code here, about 3 lines. So let's fix that. First, we apply the benchmark rule. And then all of this code becomes one simple API call, measure repeated. And we can focus on the code that we really care about. Let's check out another example here. This is a database benchmark. So first, let's initialize our database. with Room. And if you haven't seen Room before, it's another Jetpack library. It's just an abstraction over databases. All that matters really here is we're initializing some object that allows us to make database queries. So first, let's clear all the tables and insert some test data, create our measuring loop, and then we can measure the code that we care about. In this case, it's some kind of complex query, not sure what it is, doesn't really matter. But there's an issue here. Depending on your database implementation, your query could be cached, right? If we know that the query results won't be changed, shouldn't we just save that result and use that in the future instead of having to do this complex query all over again? So what we're going to have to do is we're going to have to take this clear and insert test data method and do it inside the loop, right? Every single time. Bust the cache so we can measure what we actually care about. But there's another problem here. We're now measuring more than we actually care. So what are we going to do? Well, we could do the previous thing where we take the system time, before and after, maybe save that to some variable, output the result, then subtract that from our final result, and then we'll have our actual result that we care about, right? Well, this is, again, very verbose, and fortunately, this is a common use case that we run into too. So we've created an API for this as well. And that's the run with timing disabled block. So I know a lot of Java developers out there are probably wondering, well, what about us? Well, of course, we have Java APIs as well. And it's slightly different. So I'd like to go through this line by line. A lot of code has changed here. So first, we have to create this benchmark state variable. And this is how the library is going to commute to your code when it's done. We create a while loop and call state.keepRunning. And inside that block, we can run all the code that we want to measure. If we ever need to do any setup or initialization, we can just call this pause timing method, do our initialization, and then resume when we're ready to measure again. So that's great. I've got one more example for you guys, and it's a UI example. A very compelling case for benchmarking might be UI. And we've designed this library to integrate on top of existing test infrastructure, and that's because we want you to be able to use all your favorite tools. For example, the activity test rule, which is an extraction that will help you with activity lifecycle and all the setup you need in order to make a UI test. So we simply mark this test as an @UI thread test to run on the main thread. And then we get a reference to our cycle view. Then as before, we just create a measure repeated loop and measure the code that we care about. In this case, we're scrolling by the height of one item. So let's talk about Studio integration. With Studio 3.5, we're releasing a new benchmark module template to help you get up and running with your benchmarks. So let's walk through what adding a benchmark module looks like. So here's a typical Android project. We've got an app module and a library module because we love modularization and we're great developers. We right-click the project, click New, Module, and we'll get this new create new module wizard that you've probably seen before. And if you scroll all the way to the bottom, you'll see this new benchmark module icon. Click Next, and you get this little configuration dialog you can use to choose your module name, change the package name, and we've got templates in both Kotlin and Java-based code. So click Finish, come back to the project, right? Now we have our benchmark module. Let's take a look inside. We've got an example here, benchmark here that you can just run, up and running. Similar as before, set the benchmark rule, measure repeated loop, and it works out of the box. You can just run it, and your results will appear directly in Studio, in case you're developing locally and you want to iterate quickly. We've also got JSON and XML output data. We'll pull off from connected instrumented tests from device onto your host machine. And we've done this with the intention of being ingested by continuous integration tools. So if you want to look for regressions and look for improvements you've made over time, this is a great way to do that. As with any module, there's also a build.gradle file. And there's a couple things here I'd like to point out. So first, there's a benchmark plugin that we're going to be shipping along with the library. There's a custom runner that extends off the Android JUnit runner, and it's also open to be extended in case you need to do that. And we've also pre-built it with some pre-built ProGuard rules that'll work out of the box with the Jetpack benchmark library. And of course, the library itself. Can't forget that. Very important. So let's talk about the Gradle plugin. So that's this line you saw before, the apply plugin line. It's going to help you pull your benchmark reports when you run Gradle W, connected Android test, or connected check for CI. And we've also got some Gradle tasks for CPU clock stability in there as well. The test runner, that's the Android benchmark runner. It's kind of an in-depth topic, so we'll talk more about that later. But suffice it to say, it's got a lot of baked-in tricks to stabilize your benchmarks. We've also got ProGuard rules, and that's in this file here. Our template supplies pre-configured ProGrad rules, and that's important because ProGrad optimizes your code. So you want to make sure you're running your benchmark in a configuration that represents real user performance, right? So we want to do this in a release production environment if possible. So that's why we bundle these rules for you. And we realize that tests generally don't use ProGrad or R8, but this is important for benchmarks. And it's partly why we've set it up as a separate module. So we've also included an Android manifest here that's going to run with your Android tests. And if you notice here, we've set debuggable to be false. And while this is normally enabled by default for tests, it's great because it allows us to use things like connecting a debugger and use all of our favorite debugging tools. And it's great when you're testing for correctness. But it's not so great for benchmarks. We've seen before that runs have been between 0 to 80% slower. And 80% is not the number that should be worrying you. It's the hyphen. It's the range, the variability here. It's hard to account for. Let's take a look at an example. Here are some benchmarks that we have in AOSP that we use in the Jetpack team. And along the x-axis, you'll see several different types of benchmarks that we do. And along the y-axis is normalized duration, how long the benchmark took to run. Blue is with debuggable false, and red is with debuggable on. And we've normalized each benchmark by benchmark, not across the board. So you'll see here in the deserialization example that there's hardly any difference. If you look really closely, it's like 1 pixel off, 1% difference, right? But over here in the inflate simple benchmark, there's a huge difference here. And again, the hard part here is the variability. It's really hard to account for. So we want to make sure that the optimizations and the code changes we're making are actually going to have an impact on our users. We need to make sure debuggable is off. So that leads me to about benchmark configuration. And here I'd just like to give some tips that we also bundle with the template. But you should definitely be setting up your benchmarks this way. So first, as before, we'd like to turn off debuggability. We also want to make sure code coverage is false. If you're using something like Jacoco, this actually modifies the DEX in order to support what it needs to do. And that's great if you're trying to get code coverage. But when you're running a benchmark, that's not so great. Of course, as before, you'd like to enable ProGuard. And we currently support library modules for Alpha 1. We're really pushing developers to modularize our app this year. And I'd like to do a little shout out. Please check out the How to Create a Modular Android App Architecture talk. That was on Tuesday, so you should be able to find that on YouTube. It's by Florina and Yeet. But what if you forget? As a library, we can do a lot. But we can't do everything. We can't just print out a device and have you run on that, right? But that would be great. Fortunately, we've got warnings. So we're going to corrupt your output and make it very visible to you. And hopefully this is something that you can catch in your continuous integration tests. So here's an example of some couple warnings. Debuggable as before. If you're running on an emulator, that's also pretty bad. If you're missing the runner, then you're not using any of our tricks to help stabilize your benchmarks. And if you're low on battery. Now, a surprising thing about being low on battery is that, well, you might expect the device will throttle itself, right? It'll try and save power. However, we've found that on many devices, it still does this even while it's charging. So this is definitely something you want to watch out for. So that's a bit about what the library looks like and how you would use it. And now Chris is going to talk about how it works.
All right, so that was a lot of information about what it looks like to use the library, but there's a lot of implementation behind it to implement all of these behaviors that Dustin was talking about. So first of all, let's talk about CPU clock, specifically frequency and how it's kind of the enemy of stability, because when you go up and down massively, you change results and you make it very hard to discover regressions and improvements. So from the perspective of benchmarking, there are really two problems that CPU clocks introduce to us. And the first is ramping. Clocks generally start out low when the device isn't doing anything, and then once work is scheduled, they will ramp slowly over time in order to get to a high performance mode. On the other side of this, though, when the device gets hot because it's been running for a long time, the clocks will dive quickly, and you'll get terrible performance. So both of these are problems. Let's talk about them one at a time. So first, ramping. Clocks will generally increase under load, and what we've seen is that this takes about 100 milliseconds. So here we have a clip of a little systrace here, and the only thing that's important to note is the clock frequency at the bottom versus when the work started on the top. At the very beginning of the trace, you see time equals 0 milliseconds. The frequency is 300 megahertz, incredibly slow, a frequency that most of your app code is never going to see. However, after about 75 milliseconds, you see that we go all the way up to 2.56 gigahertz. If we were measuring in between these two times, that would be bad. However, the solution for this is actually pretty simple. Benchmark just runs warm-up in order to account for this. So we spin the measurement loop for 250 milliseconds before we ever start measuring. And then we only start measuring once timing stabilizes. This also has the nice side effect of handling the Android runtime's just-in-time compilation. By the time that your performance numbers are stabilizing, JIT has stabilized as well. You're seeing performance that's corresponding to what your user would see in a frequently hot code path. So that was ramping, but diving is a much bigger problem. When the device gets hot, the clocks dive quickly, and this is called thermal throttling. Generally, the CPU will lower its frequency once it gets to a very high level because it wants to avoid overheating and damaging the chip. Unexpectedly, though, this can happen unexpectedly, though, and massively affect performance while we're running our benchmarks. So take a look at this sample where I'm just taking a pretty simple benchmark. It's just doing a tiny bit of matrix math in a loop. And at the beginning, I'm getting relatively stable performance. Over the first minute or so, it looks pretty stably at 2 milliseconds. All is well. But less than a minute in, performance becomes terrible. Look at that. Less than 2 minutes in, we are up to 3.5 times the performance that we expect. However, the device runs at this low clock for a little while. It cools down, and it's back down. OK, well, we're good now, right? No, we're still doing the work. So over the result of this 5-minute test, we have thermal throttling taking us up and down and making these results pretty terrible, right? We can't extract a whole lot of information from these because we are dynamically going between 2 and 7 milliseconds. We can't trust these measurements. So our solution to throttling, we found, is different per device because we have different tools that we can use in different configurations. So the first solution to thermal throttling is the simplest: lock clocks. What if we could just set the clock frequency? Well, unfortunately, this is ideal, but this requires root. This is not a great solution for the average person because although we can set it to a medium frequency, this will keep it from thermal throttling because the device handles medium frequency just fine. We do provide a Gradle plugin for you, though, if you do have a device that is rooted. Simply Gradle W lock clocks, and your device is locked. But requiring root, though, is really not a general solution. We don't recommend it. So what else do we have? Well, there was this API added in Android in window.setSustained performance mode. And this was originally designed for VR and for games, but it's incredibly appealing for benchmarks. This is because it lowers the max clocks specifically to solve this problem, prevent throttling. Perfect, right? And it also works on GPUs as well as CPUs, so it's even useful if you're wanting to do rendering benchmarking, say if you're a game. However, it comes along with a lot of difficulties. It's designed for VR, not for headless benchmarks. So first of all, it requires an activity running with a flag set. It also has 2 separate modes if it thinks that you're single-threaded versus multi-threaded. And it's also only supported on some N+ devices. So let's talk through each of these. Maybe we can solve some of this. So the first is the activity flag. And in order to solve this problem, we actually just launch an activity for you around any headless test. We inject an activity that launches any time that we might need to use set sustained performance mode so that it's up at all times. We set this flag also on any activities that you launch. So if you're doing a UI test, like Dustin was showing before with the recycler view, that gets this property as well. And it works together with activity test rule and activity scenario, so you don't have to worry about adapting to this new model. And in addition, it also calls it out in the UI of the test while it's running. It pops up there and says, hey, I'm in set sustained performance mode. Now, OK, so we've got a way to solve the problem of needing the flag. But how do we handle the 2 different modes? So first, let's describe what these are. The set sustained performance mode can either operate in a single or a multi-threaded mode. Either that means you have your single-threaded application, so we could probably use 1 core at max frequency, all right, or you're multi-threaded, in which case it will set all of the cores to a lower frequency to prevent throttling. That's fine for a game, but we're trying to run potentially different benchmarks with different threading models, and switching between these modes will create inconsistency. So what do we do about this problem? Like, how do we make, we really like to just pick the multi-threaded mode. That's the lower of both. That sounds good, but how do we force that? Well, the way that we do this is in our Android benchmark runner, when sustained performance mode is in use, we create a new thread. And this thread spins. And this is a really strange way to do this, but it turns out that this is actually a pretty efficient way to force us into a multi-threaded mode, and it gives us that incredibly sustained performance that we were looking for. We are also, set a thread name for it, so if you see this in a trace, you understand what's going on. And we do the best we can. We set thread priority to be the lowest possible so that it interferes with your test minimally. But here's a look of what that looks like in systrace. So on the top there, you can see clock frequency. And over the time of the benchmark running, when the test starts, the activity launches, bam, we're suddenly locked to half clocks. Perfect. We're not going to thermal throttle in that configuration. Once the test is done, the activity finishes, and then the clocks are free to ramp back up slowly over time. So we talked about how we solve the issue with having an activity running with a flag set. We talked about the two different modes, but we still have this last issue. This is only on some N+ devices. So you can check whether this is supported on a specific device by calling power manager is sustained performance mode supported. By the way, this is supported for anything that is VR certified, so you have that. However, in the Firebase test lab, for example, 11 out of the 17 Nougat Plus OS device combos have support for it, so it's not terribly hard to find something that you can use like this for CI. But again, this is still not a general solution. This requires platform support that isn't available on every phone. So our final solution to this problem, at the very end here, is thread.sleep. The simplest solution, we don't have, many devices aren't rooted, many devices don't have set sustained performance mode, so we use thread.sleep. So what we do here is we use we detect a slowdown in between every benchmark by running a little tiny mini benchmark to see if the device has started thermal throttling. If it does, we throw away the current benchmark data and we sleep to let the device cool down. So we saw this previous slide, how performance was oscillating all over the place and we couldn't get stable numbers out of this. Well, in this particular case, our device doesn't have root, so we can't use lock clocks. It can't use set sustained performance mode, not available, okay, can't use that. So we have to fall back on thread.sleep. So let's see how that actually performs in this graph. That is a lot better. It is just completely flat, and if you see here, we have standard deviation for the two different approaches. For the default, we've got 2.25 milliseconds, and for thread.sleep, if you get a look closely, 0.02 milliseconds, massively more stable, much more consistent performance. But there was a sacrifice with this. So because we were sleeping every time that we detected thermal throttling, it takes longer to run. This one takes about 8 minutes. The original takes about 4.5. So in summary, our solution for thermal strategy does have 3 different steps, and we use the best solution for your device that's available for your particular phone. So clocks are one thing, but what about background interference? What about other things running on your device? So first of all, you have to ask, am I in the foreground? So if you're not, something else is. And this is important to think about in the context of performance. Tests generally run if they don't have UI on, say, top of the launcher, because there's nothing to launch, nothing to display. However, this means that the OS thinks the launcher right now is the important app. When you're running in the background, say, for instance, behind the launcher, that means you get a lot of sources of potential performance interference. You might have a live wallpaper rendering. You might have home screen widgets updating. You could have the launcher doing hot word detection or other miscellaneous work that you don't know about. The status bar is probably repainting every now and then with like a notification coming up, the clock's changing, Wi-Fi, whatever. And starting in Nougat, it's possible for devices to have a foreground exclusive core, a core that is only available to be used by the foreground application. You just can't touch that if you're in the background. So we want to jump to the foreground, and we actually have a solution for this already, right? We have our old activity. Remember this guy? So this also solves this particular problem, and that's why we use this in all benchmark configurations, regardless of whatever your clocks are. The benchmark keeps this activity in the foreground at all times, unless you have your own, in order to guarantee that you can use all cores with minimum rendering interference from whatever's going on underneath you. But there's another important source of background interference, and that is contention. So everything on the device, from CPU to disk, is a shared resource. And if your benchmark is being, let's say, kicked off of a CPU because of some conflict with another task, if you're accessing disk and system services at the same time that someone else is, or if somebody has random background work happening, for instance, like the system doing something, an app background job, something along those lines, those can create contention. So for example, if we were running our benchmark and warm-up just finished, so we're just right about to start taking measurements. However, we have this other process here that's about to start doing some work. Our first few loops are fine, but then the other process kicks in and starts running as well. All of a sudden we see, oh, well, actually some of these loops are just giving me flat-out bad numbers, not very useful numbers, that overlap with this background work. Some of these runs are still totally fine, but some of them aren't. So that's why we have this idea of measure twice, report once. And by twice, I of course mean many times. We will measure several loops, and understanding that most contention is for a short duration, we can ignore those loops that are most likely to have hit contention. So what we do, in fact, is that we report and track the minimum number observed, not the average, because the average is susceptible to contention. This way, the number that we report by the benchmarking library is immune to tiny little hiccups that happen every now and then and might otherwise interfere with your numbers. All right, so let's talk about how to go about using this library. So the first thing that we want to recommend is don't benchmark everything. Start with tracing, start with profiling tools. Maybe you have measurement going on real user devices that tell you some particular part is slow. Well, that's a good place to start. Benchmark what you know is slow so that you can iterate on it and improve it. We generally recommend benchmarking synchronous blocks because these are the easiest to measure and these are the easiest to improve over time. So if you're measuring something that's single-threaded, it is much more likely to be stable and isolated from other tasks. There's no thread hopping. That means you're taking the scheduler entirely out of the mix. And that way, for instance, you might measure UI separately from network, separately from database and rendering. We also generally recommend fairly small blocks. These are faster to run. And here we mean probably less than 50 milliseconds. However, the loop itself only has around a 6 nanosecond overhead, and this is like running on a fairly old device at half clocks. So you can measure really small amounts of work with a benchmarking library. Another important thing to remember is that the benchmarking library is primarily for hot code. Because we run all of your code with warm-up, and we run it in a loop, that probably means that the code inside is going to be JITted. Now, that's great if it's something like work that's done by your recycler view, but if it's only run once in a while by your app, it's not as likely to get JITted. So be very careful when you're benchmarking startup. We generally recommend to only benchmark the code that is inside of a loop during startup so that it is more likely to be measured correctly. Another thing to keep in mind is to be aware of caches that might be anywhere in your code, or even in someone else's code. So here's a simple example of a benchmark where we access a file and check whether it exists. Maybe we observe that this took a couple of milliseconds during startup. The problem is that the OS is going to take this and it's going to know that nothing has changed and just serve you a cached value every time. The benchmark is going to be very different than the behavior at startup. So be aware of this. You can sometimes take measures to create things differently, for example, like Dustin showed at the beginning with the database. Another thing to consider is potentially avoid over-parameterizing. So correctness tests, it's really easy to say sweep over 5 different variables, recognize that, okay, over all 4,000 of these tests, none of them failed. Great, you get a pass. That is a much harder task for benchmarking because we're getting something that isn't a simple pass-fail. More data can be more difficult to deal with. We recommend to start targeting benchmarks at real-world parameters instead of maybe going as enthusiastically towards parameterization as you might during a unit test. One thing I really want to re-emphasize, though, that Dustin mentioned before is please do not compare devices. This library is not designed to compare the performance of one device versus another. We're really focused on comparing code, whether that's framework code, whether that's app code, on the same device, same operating system version. The library optimizes for stability. It will have some factor of difference that can vary from device to device over what you see in a benchmark versus what you see in reality. And that's because we do not account for real-world clocks. For example, if the user touches down on their device, starts scrolling, generally the clocks will ramp. If a user uses their device for a while and it gets hot and it thermal throttles, it performs poorly, the clocks go down. None of that is accounted for in the benchmarking library, and that's why we don't recommend comparing devices with our library. So you might be wondering, okay, how do I go about integrating this into my CI? So there are different tiers of adoption that you can start with to look at exactly how deeply you want to get into benchmarking. The first is quick and local. It's very reasonable to do a trace, write a benchmark, and measure the performance, make a change, check in that change without having to monitor the performance over time and detect regressions. And in general, this is because, unlike correctness tests, benchmarks usually get better because you're deleting code. Now that said, if you can monitor them over time, potentially manually, that's a totally reasonable way to go, and that's even better. But we want to recognize that there's still value in manual monitoring of benchmarks, even if you don't have regression testing, because automatic regression detection, because automatic regression detection is a complex problem. However, if you do want to go all the way to that point, and we recommend it, it is just very, it is something to recognize that it's not as simple as detecting when does my benchmark go down by, say, 1%, because there's going to be all sorts of times where it flakes a little bit, it goes down a little bit, you make a trade-off for one benchmark versus another, or you check in a feature that just absolutely needs to make this one code path slightly slower. So if you're prepared to receive emails for all those things, by all means, just something to keep in mind. All right, and so let's go through a few closing notes. We do have, as Dustin mentioned earlier, an NDK sample that shows how to use some of our infrastructure together with C++ code. That's available on our Android Performance GitHub repository, and it actually wraps the existing Google benchmark C++ library to get numbers directly from infrastructure that you might already be using for C++ benchmarking. It captures the results together with Java and Kotlin benchmarks in our file output, and it applies all of our Android-specific tricks regarding stabilizing clocks. So now Dustin mentioned that this is actually a fairly old library, so why haven't you heard of it before? Well, this library has been around since about 2016, used inside of the Android platform, and we use it all over the place. We use it for text, for graphics, for views, for resources, for SQLite, for optimizing all of these different components, but for a long time it's been very difficult to use externally because we kind of needed you to have a rooted device to run this on, and that's easy, that's easy for a platform developer, much harder for an app developer. But more recently, we've overhauled it for non-rooted devices. We've switched over to Kotlin, which gave us some really nice benefits in terms of function inlining for that measurement loop, and allowed us to minimize overhead. So now libraries such as Room, Navigation, and Slices all use our benchmarking library to make improvements. So here's an example from the platform from a couple of years ago. I think this was in O, when we noticed that, hey, toggling the visibility of a relatively large tree of views was kind of expensive. So this was our CI over the process of checking in a few changes. So at the beginning, modifying these views took 350 microseconds, and we checked in an optimization for how outlines were changed when views were stored. And so it went down a little bit, And we actually realized, like, okay, most of the work here is actually in view.invalidate. It's doing a lot of work that it doesn't need to anymore in a modern hardware-accelerated pipeline. So we checked in a complete overhaul of that. And of course, we quickly reverted it because it broke the world. But we did learn a lot of things that we needed to change along that path. And after we were able to check that back in, we were able to get a total improvement of 50% of taking that view toggling from 0.35 milliseconds per, say, 64 views or whatever, down to half of that, which is a huge improvement. And we did this all before we had automatic regression testing. So in summary here, we've seen through all of these tricks that we've talked about, benchmarking is a really complex problem. It's really hard to measure accurately. It's completely foiled by clock instability. And background interference can be a real source of pain when you're trying to detect changes. That's why with Jetpack benchmarking, we've provided a simple API. We've bundled in all the lessons we've learned about getting stable numbers out of a device. And the alpha is available now. Thank you so much for coming. If you remember only one thing, d.android.com/benchmark. Thank you all so much.